When determining the half-life of a drug, we must first figure out how many times you have to cut that amount in half. So let's look at a drug level that started out at 16 milligrams per deciliter, but ended at 2 milligrams per deciliter. As you can see, we have 16 divided by 2, which is 8. 8 divided by 2 becomes 4. 4 divided by 2 becomes 2. The original amount was cut in half 3 times within that time frame. Now if we look at the elapsed time, let's say the elapsed time was 6 hours. So 2 milligrams per deciliter was read at 6 hours after the 16 milligrams per deciliter. We would need to take that 6 hours and divide by 3 because we had 3 times that we could cut it in half. The result would be 2 hours. That would be your half-life. This is the calculation we use to figure out the concentration of an analyte in a patient's sample using a spectrophotometer. The calculation says that we need to take the absorbance of an unknown divided by the absorbance of your standard times the concentration of the standard. In this example, we're going to calculate a patient's calcium level if the absorbance of the unknown is 0.52, the absorbance of the standard is 0.60, and the concentration of the standard is 10. So first we take the absorbance of the unknown, which is 0.52, divided by the absorbance of the standard, which is 0.60, and multiply it times 10. Our answer then would be 8.7 milligrams per deciliter. The calculation for creatinine clearance is as follows. The urine creatinine multiplied by the volume in milliliters per minute divided by the plasma creatinine times 1.73 over the patient's body surface area. In this example, we are going to calculate a patient's creatinine clearance if the urine creatinine is 200 milligrams per deciliter, the plasma creatinine for the patient is 2 milligrams per deciliter, and the volume is 900 mils over a 24-hour period. The patient's body surface area is also 1.83. So first we start off with the patient's urine creatinine. As we can see, that is 200 milligrams per deciliter. We then multiply that times the volume. Because the volume is 900 milliliters over 24 hours, we take 900 divided by 1,440. Now this gives us mils per minute. We put that on top of the plasma creatinine, which is 2.0. We then multiply times 1.73 divided by 1.83. I'll go ahead and give you a minute to use your calculator to figure out the answer. Your answer for this example should be 59 milliliters per minute. For the calculation of a patient's LDL, or low density lipoprotein, we need to take the total cholesterol from the patient minus the high density lipoprotein, or HDL, minus the triglyceride level divided by 5. With this example, we're going to figure out a patient's LDL when their total cholesterol is 210 milligrams per deciliter, the HDL is 20 milligrams per deciliter, and the triglycerides are 250 milligrams per deciliter. So our LDL equals 210 minus 20 minus 250 divided by 5. This would give you an LDL for the patient of 140 milligrams per deciliter. There are a few different ways we can calculate a patient's osmolality. The first one is the osmometer, which uses freezing point depression. The second way is to use some of the patient's results from a basic metabolic panel to get a calculated osmolality. You need to be familiar with how to perform the calculated osmolality. In order to do that, you would take 1.86 times the sodium plus the glucose divided by 18 plus the BUN divided by 2.8 plus 9. Using that calculation will give you the calculated osmolality. The reference range for osmolality is 275 to 298 milliosmoles per kilogram. We find that a patient can have an increased osmolality in things such as alcohol or ethylene glycol ingestion, dehydration, or having an increased sodium or glucose concentration in their blood. We find that a patient might have a decreased osmolality if they have decreased blood sodium, excessive hydration, or a decreased antidiuretic hormone. Another parameter that the physicians might use is an osmolar gap. In order to calculate the osmolar gap, we take the measured osmolality, which we could get from the osmometer, minus the calculated osmolality, which we get from the calculation above, and that will give us our osmolar gap. If you have an increase in your osmolar gap, it can mean that the patient has alcohol intoxication or ethylene glycol intoxication, or possibly a metabolic imbalance. We can calculate the anion gap by taking the sodium plus the potassium minus the chloride plus the bicarb level. The reference range for an anion gap is 10 to 20 millimoles per liter. We find an increased anion gap in patients that could have renal failure, ketoacidosis, methanol or ethylene glycol poisoning, salicylate or aspirin overdose, lactic acidosis, low sodium, or there simply being an instrument error. Some analyzers do an anion gap to check to make sure that things are in working order. We can find a decreased anion gap in someone with hypoalbuminemia or having a low albumin, or severe hypercalcemia, although it is very rare to see someone with a decreased anion gap.